Let's continue our discussion of the runtime for Mergesort. Last time we looked at the code, or the pseudocode, I guess, for Mergesort that we had written, and we discovered this, what we call a recurrence relation. A recurrence relation for the runtime of Mergesort. You said that the runtime for Mergesort on an array of size n was equivalent to 2 Mergesort calls. It was equivalent to the runtime of 2 Mergesort calls, each on an input half the size, plus some linear amount of work, plus O of n. And so what we're going to cover in this video is the recursion tree method, or the unrolling method of solving this recurrence relation. And so our main goal here is to answer the question, T of n is equal to O of what? Right here we have this relation where we have that T is equal to some function that is dependent on T, right? And we want to eliminate that. We want just an O in there. We just want a big O runtime. So like we said, we're gonna solve this using the tree method, and you'll also hear it called the unrolling method. So how that works is there's a few big steps here. So the first one is to write out the first few levels of a recursion tree for the runtime. How it looks is something like this. We start off with a node here. Let's just make that node T of n. Right, that node just represents the runtime for Mergesort on that original array. What we're going to say is this is equivalent, this is equal, the runtime of this is also equal to the runtime of 2 Mergesorts, each of size n over 2, plus some local amount of work. So what I've drawn here is a node connected with 2 branches to 2 calls of, or to 2 T of n over 2s. Right, I've just rewritten, or I guess I've given some structure to our recurrence relation right here. So now we're gonna unroll that. We're gonna keep all of the O stuff, but we're gonna keep unrolling anything with a T in it. I just made that mistake. We're gonna unroll the things with a T in it. And so looking at this T of n over 2, we're going to apply this recurrence relation again. Right? T of n over 2, we're going to plug in n over 2 for n here. Right? T of n over 2 is equal to 2 calls of what? So we plugged in n over 2 for n here. This is going to give you n over 2 divided by 2, which comes out to n over 4. This, we're just going to plug in n over 2, and so we're going to get O of n over 2 work here. So just like we did in the first level, you're going to get O of n over 2 work, followed by 2 recursive calls to size n over 4. I'm going to unroll this one as well. O of n over 2, T of n over 4, T of n over 4. And so one important thing to realize is that these 3 trees represent the same exact information. Right? The time it takes to complete Mergesort on an input size of n is exactly equal to this local runtime we have here, this merging operation that we have here, plus the recursive calls, the two recursive calls to merge sort of the split array. And so after you've gotten comfortable with this, maybe you want to unroll this a few times. But what you're going to see is that eventually, I'm running out of space here. I'm going to make a new layer. Eventually, you're going to end up with something like this. You're going to have O of n up top. You're going to have, whoops, what's going on? You're going to have O of n up top, O of n over 2 up top, and you're going to have quarters here. Right, and this pattern is going to keep going. Right, the next level you're going to have O of n over 8s, and then O of n over 16s, and then 30 seconds. And this is going to keep going, right? So you started out with this array of length n. Maybe it's n is 1,000,000, right? And you're going to keep dividing that n by 2, by 2, by 2, all the way down. Until what? Until you've reached the base case. And if you can recall in our code, the base case for this merge sort operation, this merge sort method, was when we got an array of length 1. So when the array is of length 1, then all we're going to do is execute those first 2 lines of merge sort where it says just return that array itself. And so that, like we said before, is a constant operation, right? This base of this tree is going to be all constant operations. Right? This is going to have no 1, this is going to have no 1, have no 1, this is going to have no 1. And so one sensible question that we can ask is, let's call this h for height. What is the height of this tree? So first, let's identify the pattern that's going on here. Right? We're going to divide n by 2. How many times? We're going to divide n by 2 h times. Right? Like we said here, at each step, we're dividing, or we're splitting our array in half, and we're splitting our array in half h times. So one way we can write that is that n over 2 to the h. Let me write that more clearly. N over 2 to the h. N divided by 2 h times. When is that going to stop? That stops. We're going to keep dividing by 2 h times. And at the hth, I guess, the hth split, we're going to have an array of size 1. And so what can we do with that? Well, we can multiply by 2 to the h on both sides. Say that n equals 2 to the h. And then using log rules, we have that h equals log base 2 of n. And usually you'll see that in computer science, we don't even have a base here, right? Writing a log without a base is implying a base of 2. And so now, like I said before, we define this tree, we defined all of these trees. We drew all these trees, which were all equivalent to each other. And so our original goal, which was to solve for t of n in terms of O, well, now we do have everything in terms of O here, right? There's nothing in terms of t here. And so our job now is just to add up all of these nodes of this tree. So our new goal here, is to add the nodes of the tree. And so after staring at this maybe for a few minutes, you might notice this trick that we can apply here, right? We're looking to sum up all of the nodes of this tree, and maybe we want to find a quick way to do it, or an efficient way to do it. And one way is by realizing that each level added together, each level sums to O of n, right? 4n over 4 is here, 2n over 2 is here. The next level will be 8n over 8 is here. So whatever is in the denominator will get canceled out, and you'll just be left with an O of n. You can also make the same argument for this last layer here, because how many leaves or how many nodes are in this last level, right? How long is this? Let's call this L, the length of the number of leaves. I'm just going to do some scratch work here. Right, we're gonna take two. We're gonna start with one. We're gonna start with one node. And what's our rule for the number of nodes in each level? Well, the number of nodes in each level doubles every single time we go down a level. Right? So it follows that the number of nodes in this last level is 2 times 2 times 2 times 2 times 2 for every single level of the tree. In other words, 2 to the h is the number that we're looking for. We're going to multiply 2 by itself h times. We're going to double the number of leaves, or the number of nodes in each level h times. This is equal to L. L is equal to that. And so we already figured out what h was, right? So we're just going to plug in h. And if you remember your log rules here, that comes out to n, which is O of n. So we can make this argument really that each level sums to O of n for every single level. Right, and so now whereas before we had this giant problem of how do I sum up this tree we have here, all these O's that we have in this tree. Well, now our job just got a lot easier. We realized that at every single level we have O of n work. It sums to O of n. And so adding the nodes of the tree is now becoming the equivalent of adding O of n. Right, we're going to add O of n how many times? Well, there's h levels, so we're going to add O of n h times. And this is the equivalent of saying O of n times h, where if you remember before, we saw that h was log n, log base 2 of n, and that is equal to O of n log n. And so to reiterate, our goal is to add the nodes of the tree to find the runtime. We found that the runtime t of n, the runtime to run Mergesort on an array of size n, is big O of n log n.